Final checkout of the second Saturn flight vehicle, SA-2, was completed during this report period at the Marshall Space Flight Center in preparation for its scheduled flight testing at Cape Canaveral next quarter. The recently completed pressure test cell facility was placed into operation for the first time as the SA-2 booster underwent an extensive testing program in which high-pressure air, helium, and nitrogen were used to check tanks and mechanical systems for leakage. Pressure levels up to 3,000 pounds per square inch above normal atmospheric pressure were employed in the checkout procedure. While SA-2 checkout continued, modification work performed at Todd Shipyards, Houston, Texas, on the Saturn-carrying barge Promise, formerly named Compromise, included addition of an arched cargo cover, a pilot house, ballast system, cruise quarters, firefighting equipment, and heating system. At Wheeler Dam on the Tennessee River, 48 miles from Marshall, a mammoth repair job neared completion on the lock which had collapsed last June, forcing a temporary change in Saturn transportation plans. The Tennessee Valley Authority announced that it hopes to reopen the lock by April 23rd. Reopening will allow resumption of normal traffic, including barges carrying Saturns, beginning with SA-3. By mid-February of this report period, the SA-2 flight vehicle had finished its checkout and was undergoing final preparation for shipment to the Cape. Like its predecessor, SA-1, this vehicle consisted of a live booster, or S1 stage, with inert S4 stage, S5 stage, and payload. On February 16th, the SA-2 dummy upper stages and payload were loaded onto the Saturn barge Palaemon. These were carried as far as Wheeler Dam early next morning, and the barge returned for the booster. Loading time for the giant booster at the Marshall dock was only 10 minutes. At Wheeler, the units were transferred by land around the broken lock and put aboard the waiting Promise, which would take them the rest of the way. Only about an hour was needed to unload the booster, move it the 1 mile overland, and load it again. On February 27th, the Promise reached its destination, ending a 2,200-mile voyage, which had taken it through waters of the Tennessee, Ohio, and Mississippi rivers, the Gulf of Mexico, and the Atlantic seaboard. At the Cape Canaveral dock, the SA-2 stages were taken off the barge. After being transported overland to the launching pad about 2 miles away, the booster was erected on the launch pedestal. Shortly afterwards, mating of the inert S4 stage to the booster began. Followed by the S5. And finally, the payload, a Jupiter nose cone and aft section. The fully assembled SA-2 vehicle was ready to begin undergoing the long series of checkouts and preparations which will precede its flight testing next quarter. Assembly of the booster for the third Saturn flight vehicle, SA-3, was completed at the Marshall Center on January 8th. And pre-static checkout of the stage was finished near the end of the report period. Checkout work included testing to determine mass moment of inertia. The test is based upon application of the basic spring pendulum principle. The period of vibration for the booster, suspended on springs of known spring constants, is determined by a photoelectric cell and electric timer. The mass moment of inertia is calculated from this data, plus weight and center of gravity data obtained by electronic load cells in previous tests. A series of 3 static test firings was conducted during this report period with the SA-T3 booster, a test stage modified to specifications of the SA-3. Later, this test booster was removed and the actual SA-3 installed for static firing. Assembly of the booster for the fourth Saturn flight vehicle, SA-4, began on January 2nd and is expected to be completed this summer. Marshall's Saturn assembly area was being expanded this quarter to make it 1/3 again larger. The expanded area will house a new C-1 assembly station. One of the 2 present stations will be converted for assembly of C-5 ground test vehicles. The additional area will also provide more office space, a new electrical shop for cable assembly, and a new clean room facility for cleaning of tubes and other delicate components. In the Saturn fabrication area, retooling is now underway in preparation for structural fabrication of the SA-5 configuration or Block 2 tail section, spider beam assembly, instrument compartment, and second stage adapter. Work will be performed on 5 flight boosters plus 2 test boosters to be used in structural and dynamic testing programs at Marshall. Part of the shop is also being converted for research, looking toward fabrication methods to be used on the advanced or C5 Saturn configuration, including out-of-position horizontal and vertical welding. A full-scale mock-up of the forward and aft sections of the Block 2 or SA-5 type Saturn booster is nearing completion for use by engineers in design verification and also to familiarize assembly personnel with the new configuration. Block 2 vehicles, which will test live S-4 stages and boilerplate Apollo spacecraft, incorporate design changes necessary to accommodate manned missions. Modifications include attachment of 4 large fins at the tail to increase flight stability. The launch pedestal will be modified to accept the fins. 4 so-called stub fins, actually support structures with aerodynamic fairing, are incorporated to provide additional support points. The leading edges of 3 of the stubs will carry hydrogen ducts through the inside. Elongated fuel and LOX tanks will hold some 100,000 pounds more propellant for a longer burning time. 2 large spheres filled with gaseous nitrogen will replace the 48 smaller spheres used on Block 1 to pressurize the booster's fuel tanks. The booster's honeycomb fairing used to fair in between the booster and S-4 stage is mounted to the I-beam, as are the 4 retro rockets. Attaching the upper stage directly to the spider beam eliminates need for the Block 1 upper stage adapter. Another model, this one built to a scale of 1 to 10, depicts a Block 2 booster and a cutaway version of the S-4 stage carrying an Apollo spacecraft on top. Fabrication of the 70 and 105-inch fuel and LOX tanks for Block 2 Saturn vehicles is now underway by the contractor, Ling Temco Vought, at its plant near Dallas, Texas. Manufacturing begins at this skin mill. Flat material is properly dressed prior to rolling it into cylindrical skin configurations. The tank dome bulkheads are shaped by using a technique called hydrospinning. Then, the finished units are carefully inspected for uniform thickness by using this semi-automatic Vidi gauge. Prior to in-line assembly, each tank section is trimmed to a specified close tolerance using this modified lathe. Z-frames are uniformly spaced between the tank segments, then joined by spot welding the frames to the segments with this precision welder. To prevent assembly line bottlenecks, a portable X-ray unit is used to check the condition of smaller parts. Weld specimens and tank segments are inspected at each station point of the tank just before final cleaning and testing. Meticulous care is exercised during the cleaning of these locks and fuel tanks. Then, they are rigorously tested in the hydrostatic test stand as a final proof of overall reliability. Activation of Marshall's Michoud operations plant near New Orleans was underway this quarter. The huge facility is being made ready for use by Chrysler Corporation, contractor for production of future C-1 boosters, and by Boeing Company, contractor for development and production of the advanced Saturn booster S-1C. The activation job is being done by the New Orleans firm of Gertler, Hebert and Company. The work consists generally of inspecting, repairing, and returning to usable condition the vast manufacturing building, covering nearly 2 million square feet of floor area, and an adjoining office building, plus certain work on the grounds. At Douglas Aircraft Company, contractor for the S-4 stage, initial cold flow tests have been successfully accomplished with both liquid oxygen and liquid hydrogen. Designed to check out the fuel and oxidizer systems, these tests consisted of transferring LOX and LH2 from the storage area through the ducting and valve complexes into the battleship tank. All aspects of the system performed properly. This full-scale engineering mock-up of the S-4 stage will be used to functionally check the vehicle's electrical system and its compatibility with ground support equipment. Many of the mock-up's electrical wiring harnesses have been completed, and a large percentage of the wiring has been installed in preparation for the system's integration testing program. Completed in January, this hydrostatic test vehicle is the first S-4 stage using manufacturing techniques designed for flight vehicles. It is currently being put through a series of hydrostatic filling and pressurization test operations using water for the test liquid. On the final test, it will be pressurized to destruction. At Marshall, a comprehensive liquid hydrogen test program, indicative of the increasing importance of LH2, was underway this quarter. This metal tensile strength test is conducted by immersing test samples into LH2. Metals used for S-4 stage fuel tanks, transfer ducts, and fuel pumps are tested and evaluated by mounting them in this cryostat. The cover is then securely attached, and the sample is pre-cooled by use of liquid nitrogen to minus 320 degrees Fahrenheit. After desired temperature has been attained, the liquid nitrogen is drained, and the sample is further cooled to minus 420 degrees by using liquid hydrogen. The liquid hydrogen is drained, and the sample is subjected to a tensile strength test. Since the use of liquid hydrogen in rocket propulsion is still relatively new, extensive experimentation is necessary to determine its compatibility with related components. At another facility, liquid hydrogen pressurization tests are run to determine the effect of varying the temperature of the pressure and gas and drain time of the tank on the amount of pressurization gas required. LH2 is transferred from the storage area through vacuum-jacketed lines to the test tank, a double-walled aluminum container with vacuum space between walls for insulation purposes. The pressurization gas is cooled by liquid nitrogen when low-temperature gas is required, and heated by a DC current electric heater when high-temperature gas is needed. Flow rates, temperatures, liquid level, and pressures are recorded to obtain data which indicates the most efficient pressurization method. Another liquid hydrogen test facility is now being used to familiarize Marshal personnel with handling LH2 in large quantities and will be used next quarter for static firings of Pratt & Whitney RL-10 liquid oxygen, liquid hydrogen engines. Cold flow tests, in which propellants are run through the engine but not ignited, were carried out this quarter to measure propellant flow rates, pressures, and other vital functions. Flow tests had been conducted previously to transfer the liquid hydrogen from a 7,800-gallon trailer tank to the test stand's 2,200-gallon run tank. In conjunction with engine cold tests, steam evacuation system tests were also run, in which steam was used to pull a vacuum on the test stand's diffuser system, simulating outer space pressure conditions. Looking to the future, this artist's conception shows a new test stand scheduled to be built at Marshall for work with liquid oxygen, liquid hydrogen engines. This large low-pressure environmental chamber is being used at Marshall to simulate outer space conditions for the RL-10 engine in a series of tests studying means of gasifying pre-ignition liquid oxygen chill-down flow to reduce explosion hazards. The method being evaluated is the injection of gaseous nitrogen through a manifold into the LOX exhaust stream at the engine's nozzle exit. Due to ease of handling, liquid nitrogen is being used in these tests to simulate LOX. During flight, before engine startup, propellant flows are necessary to pre-cool pumps and feed lines. The liquid hydrogen chill-down flow will be vented overboard, and LOX will be exhausted into the booster S4 interstage area. Ambient pressure there may be below the triple point of oxygen, forming solid particles. It is anticipated that the oxygen, whether solid or liquid, can be evaporated using the sensible heat from gaseous nitrogen injected just below the thrust chamber. This test, photographed at about 3 times normal speed, shows liquid nitrogen being exhausted in the form of solid particles. When a specified gaseous nitrogen flow rate is injected into the solid stream, the result is a heat transfer between the gas and solid, causing evaporation. After optimum gaseous nitrogen flow requirements are reached in future tests, the system will be tested on a hot fire engine at Douglas or Pratt & Whitney. Typical of continuing varied research projects at Marshall are experiments in magnetic forming and electric discharge forming in a fluid state. Ultra-fast discharge of voltage from this capacitor bank and supporting circuits through this large coil provides the shock wave to form metal into predetermined shapes. In preparation for magnetic forming, a blank piece of metal stock is placed over the coil. Then the system is energized. Because of the overload of current, the system discharges rapidly and the resulting shock wave shapes the metal stock. This method promises to be valuable in forming metals for advanced Saturn vehicles, as well as providing means for making space vacuum seals and facilitating fabrication in space. This equipment is part of a new photographic instrumentation system known as fiber optics, being developed for Saturn. It will be flown for the first time aboard SA-5. Filming during flight will be accomplished through use of a Millikan instrumentation camera. The optical cable consists of a bundle of extremely fine glass fibers arranged so that when an image is imposed on the face of one end of the cable, the image is conducted to the opposite end and reconstructed on its face. The objective lens must be accurately focused to ensure a clear image of the subject. In this test, a small propeller. Camera lens adjustments are made by using the bore sight fixture, allowing for a clear picture between camera and near-end lens. The use of optics cables enables camera mounting other than at the point of image. Useful applications in flight are filming the forward sections from the booster, where several fields of view are required to determine rate of separation and to study behavior of the forward section relative to the booster. The camera is now filming the motion of the solar cell-driven propeller. The optics cable has carried the image back to the camera for film recording. Saturn flights will be monitored by 8 of these systems. A new approach to obtaining three-phase, 400 cycle per second power from batteries is being developed and refined at Marshall. This static inverter will supply power for the ST-124 stabilized platform carried aboard the SA-3 vehicle. The circuitry consists of a frequency standard binary countdown flip-flops, logic elements, power amplifiers, output transformers, and a magnetic amplifier type voltage regulator. The static inverter has no moving parts, consequently no mechanical wear. Cabling requirements are reduced, as well as physical size of the battery. Pound for pound, the static inverter is much more efficient than a rotating inverter. This breadboard circuit is a higher-powered version of the static inverter, and when properly packaged, will be used on future Saturn vehicles. Power transistors are used in their most efficient mode of operation, that is, as switches. The output voltage wave is stepped and closely follows a sine wave, having only a 10% total harmonic distortion without fluttering. As research and development for future Saturn vehicles moved ahead at Marshall and its contractors across the nation, the ultimate test, actual flight, was nearing for SA-2, poised for its attempt to match the spectacular success scored last October 27th by the first Saturn ever launched.